In the following video, I will briefly introduce the idea of multiple CPU systems, what are they exactly, in what cases can we utilize them, and how to do it in practice. So what exactly is multiple, or to shorten multi, CPU system? Well, imagine a PLC setup where we have a base plate with power supply, main CPU, and perhaps some modules. Quite understandably, we can have a number of such modules placed on those general purpose, for now empty, slots. But there may be applications or requirements where usage of yet another CPU or some dedicated robot or motion CPU may be inevitable. This generally should arise a question: do we have to split it all between a few base plates and figure out a way to reliably communicate those CPUs? Or perhaps there is some more clever and also cheaper way to do so. As you may already have guessed, yes, there is in fact dedicated functionality to address such requirements. When using IQ and IQR platforms, one can easily combine multiple CPUs of the same or different types on the common baseplate, utilizing fast and undisrupted data exchange through the shared memory area. There are multiple cases when configuring a multiple CPU system is advised. Those include number of high-accuracy motion-related tasks, as well as shortening the scan time of entire system by distributing control of I/O points among multiple CPU modules. To summarize, multi-CPU system is a configuration based on load distribution. By distributing such tasks as servo control, machine control, and information control among multiple processors, the flexible system configuration can be realized. Overall system responsiveness is improved by distributing tasks that require high load processing over several CPU modules. So what types and how many CPUs can we exactly combine together? The CPU module can only be mounted on the main base unit, and maximum number of mountable CPU modules is up to 4. The following table shows possible combinations, where the leftmost column describes which CPU can be used as main one, placed on dedicated CPU slot. Based on selection of that main CPU, the possibilities of attaching the following ones are a subject of change. So, for example, it is not possible to use robot CPU as main one, as it's missing from the left column. But such robot CPU, or in fact up to 3 of them, can be used together with standard R CPU or a safety one. Please make sure to always refer to IQR module configuration manual for most up-to-date information. Going back to how are the CPUs numbered, as we already know, at the leftmost position there is a main CPU. Then we have the rest of the system. But looking at the base plate itself, we can discover that in fact additional CPUs are mounted on standard slots. There is only one CPU slot and it is always occupied by the main unit. CPU numbers allow for identifying the CPU modules on the multiple CPU system. The CPU module mounted on the CPU slot in the base unit is always CPU number 1. Then the following CPUs, so number 2, 3, and 4, are sequentially assigned starting from the module on the right side of CPU number 1. With multiple CPUs mounted on the base unit, each of the CPU modules control their own assigned I/O modules and intelligent function modules. In addition, the CPU modules communicate with each other. In such system, a control CPU must be set for each module. If the control CPU is not set, it is always CPU number 1 that controls all the modules. CPUs are assigned with I/O numbers as well, as shown in the table. So, in the sample shown on the screen we have CPUs, then modules, and that is a rule. We cannot attach neither standard nor intelligent modules in between of the CPUs. So, does it mean that CPUs are always placed on CPU slot and then I/O slot 0, 1, and 2? Well, not necessarily, as there is also possibility to reserve CPU slots. The CPU reservation mechanism allows for leaving an unoccupied slots in between, which may be used to reserve such space for the future additions to the system if there are plans for such expansion. In such case, CPU number is assigned here, meaning reserved. Nevertheless, even though there is no physical CPU mounted, or at least not yet. The memory structure of multiple CPU systems consists of buffer memory, which is utilized for data communication between the CPU modules. That buffer memory is then divided into certain areas utilized in one of multiple mechanisms of data transfer. CPU modules within a multiple CPU system can transfer data to each other by a refresh mechanism or through direct access. Size of data which can be exchanged within fixed scan intervals is a limited fraction of the overall CPU buffer memory area. The communication methods are generally divided into two types. One where data is transferred at individual timing of each CPU module, and the other one where fixed scan communication is imposed on the whole system to adjust timing between CPUs. The latter one, called fixed scan communication, allows for specifying fixed interval for data transfer. This interval can then be synchronized with the timing of inter-module synchronization cycle. Additionally, the memory configuration of existing system can be checked directly in JXWorks 3 software. Switching to JXWorks 3, configuration of multiple CPU system is rather straightforward. Before we proceed to the configuration, we have to figure out how to connect to such multiple CPU system. So, when specifying connection destination, we always have to use the IP address of the module of the CPU which we are physically connected to. So, for example, even if we want to access CPU number 2, number 3, or number 4, but we are physically connected with our Ethernet cable to CPU number 1, we should use IP address of that first CPU, but then at the very end of this configuration window, we have possibility of choosing target system, which can be not only CPU 1, but for example CPU 2, 3, or 4. So after we have set up our configuration of host CPU, in order to successfully run such multi-CPU system, the configuration of all used CPUs must be compliant. Namely, multi-CPU configuration, fixed scan cycles, I/O fetching, etc. need to be the same for the host CPU and all subsequent CPUs. Regardless of whether you already have such a system and just want to read online configuration from PLC or prepare your own configuration using available elements in element selection window, the gist of whole configuration is just the same. After reading online configuration or dropping CPUs of your choice into the project, you should take a closer look into the parameter window where you will find system parameter. Inside of system parameter window, you have three tabs to set up the multiple CPU system. First of them being I/O assignment. And in I/O assignment, you should take a closer look at I/O assignment setting. That's where you can set control PLC, control CPU setting for each individual module that you have attached in your system. So here, for example, my input and output module number 1 is connected to PLC number 1, but then the second output module is connected to PLC number 2 as control PLC. This setting defines which of the CPUs hold the control over specific IOs. Then we have multiple CPU setting. Inside of this window, you can look up the CPU buffer memory setting together with direction display between CPUs, showing you how the data is being sent and received over fixed scan communication. You can turn on this fixed scan communication and define the area size for each of the CPUs, as well as you can set the fixed scan communication time and possible cooperation between fixed scan communication function and inter-module synchronization function. The following settings define behavior of each individual PLC in case of error occurrence, synchronization of their startup, as well as I/O fetching function, which allows us for readout of signals of I/O points controlled by the other CPUs. And the last tab allows us to use inter-module synchronization setting, which is not within the scope of this video, so I will just leave it for now. So in general, it's quite straightforward, but there may be cases where we need to put a little bit more attention to our system configuration. So, for example, let's take the safety CPU. Setup of such multi-CPU system where safety CPU is our host PLC will require putting all CPU modules in between the main safety CPU and safety function module. Then from the JXWorks perspective, it's pretty much the same. So in such case, after reading the configuration, of course, our second CPU will be placed in between the safety CPU and safety function module, but the rest of the configuration remains pretty much the same. Safety CPU may be mounted together with standard CPU in case one would like to obtain functionalities not available in safety CPUs by default. In practice, it is mainly tied to communication limitations where, for example, safety CPU does not support syslink iField basic, but standard CPUs are not the only type to combine with safety CPUs in multiple CPU system. There is a solid number of applications where safety CPUs are used on the common baseplate with, for example, robot CPU. It is worth noting here that in case of safety CPU, fixed scan setting time is limited to no less than 1 millisecond, which may cause inability to use some of mounted CPU's possibilities. For example, coordination control in robot CPU, which requires scan time of no longer than 0.88 milliseconds, cannot be used together with safety CPU as it imposes scan times of not less than 1 millisecond. Things are getting little different with RN-EN CPU. While physically this CPU is one double slot unit, in multiple CPU configuration the network part is placed at the rightmost position. When read module configuration from PLC is performed while parameters are not configured, module configuration is read according to the actual system. In that case, change the position of the RN-EN CPU of its network part to the right of the rightmost CPU. After setting parameters, the module configuration diagram keeps the setting of the parameters even though read module configuration from PLC is performed. Likewise, when read mounting status is performed while parameters are not configured, I/O assignment setting is read according to the actual system. In that case, change the position of the network part of RN-EN CPU to just below the last CPU on the list. After setting parameters, the I/O assignment keeps the setting of the parameters even though read mounting status is performed.